We open on a scale model of the bridge, not sitting placidly, but being tortured. In a cavernous wind tunnel facility, the lead engineer watches as a 1:40 scale section begins to shudder violently under simulated 200 km pro Stunde winds. It's not just bending, it's entering a harmonic death spiral. The model twists, then shears from its moorings with a sickening crack. In the observation room, the engineer removes his glasses and rubs his eyes. So, a voice asks from the shadows, paperwork says this design is uncollapsible. He doesn't look up. Paperwork, he mutters, gesturing at the wreckage, has never been to the South China Sea. The camera holds on the twisted miniature, a graveyard of good intentions, as we cut to the churning waters of the real typhoon gauntlet. We open on a scale model of the bridge, not sitting placidly, but being tortured. In a cavernous wind tunnel facility, the lead engineer watches as a 1:40 scale section begins to shudder violently under simulated 200 km pro Stunde winds. It's not just bending, it's entering a harmonic death spiral. The model twists, then shears from its moorings with a sickening crack. In the observation room, the engineer removes his glasses and rubs his eyes. So, a voice asks from the shadows, paperwork says this design is uncollapsible. He doesn't look up. Paperwork, he mutters, gesturing at the wreckage, has never been to the South China Sea. The camera holds on the twisted miniature, a graveyard of good intentions, as we cut to the churning waters of the real typhoon gauntlet. The mud isn't just soft, it's deceptive. A core sample pulled from 30 meters down looks like gray toothpaste, and when a technician squeezes it in his bare hand, it oozes between his fingers and drips back into the sea. That's our foundation, he says flatly. The engineering team knew immediately that conventional bridge piers, the kind that sit on the seabed like table legs, would simply sink into this geological jelly until the entire structure tilted and vanished. What they needed was something that ignored the mud entirely. The answer came in the form of colossal steel caissons, hollow cylinders 120 meters tall and as wide as a basketball court, fabricated onshore and floated into position by tugboats. Each one is a building turned on its site, with walls thick enough to shrug off a ship collision. The 3D animation reveals what the naked eye never sees. Once positioned, valves open and seawater floods the interior chambers. The caisson begins its descent, slowly at first, then accelerating as it slices through the soupy ooze. For the first 25 meters, it requires no driving force at all, gravity alone pulls it through the mud like a blade through custard. Then comes the transition zone, where the sediment thickens into dense clay. The resistance spikes. This is when the hammers begin. The hydraulic impact hammer arrives on a specialized vessel, a floating anvil the size of a locomotive suspended above the caisson's crown. When it strikes, the sound doesn't carry through the air so much as through the water itself, a concussive thump that vibrates through the hulls of nearby ships and into the chest cavities of every worker within a mile. The animation slows time to show what happens below. Each 1,200 kilojoule blow sends a pressure wave racing down the steel walls, compressing the mud outward like a shockwave through flesh, and driving the cutting edge 3 mm deeper. 1 blow, 3 mm. 20 blows, 6 cm. A full day of relentless hammering, 2,500 strikes delivered with metronomic precision, gains perhaps 2 meters. The steel groans but doesn't buckle. The goal lies 30 meters below, where the mud finally gives way to weathered granite, bedrock that hasn't moved in 200 million years. When the caisson's teeth bite into that stone, the entire acoustic signature changes. The dull thud becomes a sharp, ringing ping that echoes back up through the cylinder. On the surface, the engineers monitoring seismic sensors break into exhausted grins. The pile has refused 90% of the blow's energy, meaning it has found something immovable. They'll hammer for another 2 hours anyway, driving the caisson 3 meters into the granite, mechanically keying it into the skeleton of the planet. 120 of these would be needed. The first one took 6 weeks. If the mud was a problem of brute force, the wind demanded something closer to deception. The archival footage flashes up without warning, grainy black and white film from November 7, 1940. The Tacoma Narrows Bridge, nicknamed Galloping Gertie, undulating in 67 km pro Stunde wind. The deck twists like a ribbon, the suspension cables whipping in wild asynchronous patterns, and then the center span simply tears itself apart and crashes into Puget Sound. A dog trapped in a car is the only casualty, but the engineering world was permanently traumatized. The culprit was identified as aeroelastic flutter, specifically vortex shedding, where wind passing over a bluff structure creates alternating low-pressure zones that induce oscillation. A straight bridge spanning 36 kilometers of open water would present an unbroken face to the prevailing typhoon winds, inviting exactly this phenomenon at a scale that made Tacoma look like a toy. The solution was so counterintuitive that when it was first proposed, several senior engineers laughed out loud. Make the bridge deliberately crooked. Not a gentle curve for aesthetics, but a calculated, serpentine S-bend that forces the wind to constantly renegotiate its relationship with the structure. The wind tunnel split screen tells the story more vividly than any equation. On the left monitor, a perfectly straight bridge model, 1,5 meters long, faces a 180 km pro Stunde Extrem. Within seconds, small vibrations begin at the leading edge. Within 10 seconds, those vibrations have organized into a standing wave, the deck bobbing in a sinusoidal rhythm. At 22 seconds, the oscillation amplitude exceeds the model's structural tolerance and it snaps at the midpoint, polystyrene fragments peppering the tunnel walls. On the right monitor, the S-curve model faces identical conditions. The wind strikes the first arc and is deflected downward, creating a turbulent boundary layer that hugs the deck. At the second bend, it encounters a different angle of attack, and the vortices that try to form are disrupted before they can synchronize. The model trembles slightly, a high-frequency shiver rather than a building oscillation, and remains intact. The engineer watching both screens doesn't celebrate. He simply writes something on his clipboard and orders the test repeated at 220 km pro Stunde, 250, 280 at 300 km pro Stunde. The curved model finally begins to show dangerous movement, but by then the wind speed exceeds anything recorded in the bridge's location by a 500-year margin. The S-curve had done something elegant. It didn't fight the wind, it confused it. Every typhoon that would strike this bridge would find itself fighting a structure that refused to present a consistent opponent, a shapeshifter made of steel and concrete. You cannot confuse a typhoon at sea. You cannot hammer caissons into granite at sea. You cannot pour 8,000-ton concrete segments at sea. So you don't build the bridge at sea at all. You built it on land, in pieces, and then you carry it out. The factory complex constructed for this purpose occupies reclaimed land larger than Monaco, a cluster of aircraft hangar-sized sheds where the bridge is being born in 23-meter segments. Each segment is a self-contained universe of rebar and concrete, requiring 300 tons of reinforcing steel bent into precise geometries by workers who look like ants crawling over the skeletons of prehistoric creatures. The concrete pour for a single segment requires 80 mixer trucks arriving in staggered convoys, delivering 1,200 cubic meters of high-performance concrete in a continuous 18-hour operation. If the pour stops for more than 45 minutes, the cold joint that forms will create a structural weakness that could propagate into a crack decades later. So they don't stop. Night pours are lit by halogen flood so intense that workers wear sunglasses at 2 Uhr nachts, and the steam rising from the curing concrete creates its own microclimate inside the shed, a humid fog that condenses on steel beams and drips back down like artificial rain. The segment, now weighing more than a fully loaded container ship, must then be moved. The transporter vehicle that accomplishes this has 512 wheels, each one independently steerable and computer-controlled. It doesn't drive so much as glide, a millimeter per second crawl toward the waiting barge, while a laser guidance system tracks its position relative to the quay edge with sub-centimeter precision. The barge is the Tianyi, and calling it a crane vessel feels like calling a cathedral a room. Its lifting capacity is 12,000 tons, and it accomplishes this with two massive A-frame gantries that rise 120 meters above the waterline, their steel latticework so dense that from a distance they appear solid. When the Tianyi lifts, the world holds its breath. The segment rises from the transporter, and the barge's ballast system immediately compensates, pumping 3,000 tons of seawater between internal tanks in a matter of seconds to maintain stability. The segment swings out over the open ocean, and now the real ballet begins. Satellite positioning alone isn't enough. GPS has a margin of error of a few centimeters, and a few centimeters in bridge construction is the difference between a stress-free structure and one that will tear itself apart over a decade of thermal expansion. The Tianyi operates within a local positioning network, a constellation of laser total stations on fixed platforms that triangulate the segment's location to within 3 mm. The crane operator, a man who hasn't had a full night's sleep in 18 years, moves the segment with control inputs measured in fractions of a degree. His hands on the joysticks barely seem to move, but 8,000 tons of concrete and steel respond by drifting the final 2 meters toward its waiting neighbors. The gap between segments is specified as 15 mm, enough to allow for thermal expansion but tight enough to maintain structural continuity. The segment touches down, and the team moves in immediately to weld the temporary connections. The entire sequence, from liftoff to touchdown, has taken 6 hours. They will repeat it 2,700 times. 20 miles offshore, the accommodation platforms rise from the sea like industrial oil rigs, but they serve a different purpose. These are floating towns housing 3,000 workers who operate on 28-day cycles, 4 weeks on the platform, 2 weeks at home. The commute isn't a commute, there is nowhere to go. The platform has a canteen that serves 4 meals a day to cover all shifts, a medical clinic equipped for everything from welding flash burns to cardiac events, and a single recreation room where the television plays dubbed dramas from the mainland on an endless loop. The real architecture of the place is psychological. The designers included a corridor deliberately longer than any other on the platform, a 200-meter straight shot along the accommodation block's long axis, specifically so workers could walk in a straight line and feel distance moving beneath their feet. Without it, the constant confinement created a spatial claustrophobia that previous projects had learned to fear, men losing their sense of scale and proportion, the horizon becoming an abstract concept rather than something experienced. Salt is the constant enemy. It gets into everything. It crystallizes on exposed skin within minutes of stepping outside, a fine white powder that accumulates in the creases of elbows and behind ears. It corrodes the steel railings so aggressively that they must be replaced every 18 months despite protective coatings rated for 20-year service on land. It clings to the welding rods and contaminates joints if the rods aren't stored in humidity-controlled cabinets opened only at the moment of use. The workers taste salt on their lips constantly, in their food, in the moisture they breathe at night. Their boots disintegrate within 3 months, the stitching dissolved by the chemical marriage of sodium chloride and constant damp. The platform is a testament to human endurance, but it extracts a price. In the quiet moments, the camera finds the spaces the official documentary might avoid. A man sits on the edge of his bunk at 3 Uhr nachts, holding a phone that displays a photo of 2 small children and a woman standing in front of an apartment building in a city 1,200 kilometers away. The connection is satellite-based, and it costs a month's wages for a few hours of patchy video calls. He doesn't speak. He just looks at the photo, rotates the phone so the screen dims but doesn't lock, then looks again. In another room, a younger worker writes in a notebook, not a journal but a careful accounting of days remaining, each page a grid of small squares filled in with a pencil. Half the squares are shaded. When the book is full, he will go home. An older worker, a welder with 40 years of experience and a face weathered to leather, sits alone in the canteen long after the meal service has ended. He's looking at nothing in particular, but when asked what he's thinking, he says without hesitation, that I've built 4 of these. And my son will build the next one. And neither of us will ever cross this bridge as anything but a worker. The camera holds on him for a long moment, the fluorescent lights buzzing overhead, the distant thrum of generators penetrating even this moment of stillness. Then he stands, pulls on his salt-stained jacket, and walks out into the corridor where the sea wind whistles through the ventilation grates, heading toward the night shift, heading toward the arc light, heading toward the impossible. The shipping lane is a monster that doesn't care about human ambition. Every day, 4,000 vessels transit this stretch of water, from fishing trawlers to 400,000-ton supertankers drawing 20 meters of draft, their hulls loaded with crude oil, liquefied natural gas, and containerized cargo worth more than the GDP of small nations. The channel is 30 kilometers wide but only a narrow central corridor is deep enough for the largest ships, and that corridor happens to intersect the bridge's most logical path at a near perpendicular angle. The math is brutal. A fully loaded VLCC supertanker traveling at 15 knots possesses kinetic energy equivalent to a small nuclear weapon. If such a vessel struck a bridge pier, the pier would cease to exist, and the resulting collapse would cascade across multiple spans, dropping hundreds of vehicles into the sea. The environmental catastrophe alone, tens of thousands of tons of bunker fuel spilling into a marine ecosystem, would eclipse the structural loss. Pillars in the shipping channel are not an option. They are a declaration of war against probability, and probability always wins. The engineers had to make the bridge vanish. Not metaphorically, but physically. At the precise point where the bridge deck meets the shipping channel, the road must leave the air and descend into the seabed, traveling the remaining distance in darkness. This transition cannot happen gradually over kilometers, it must occur within the tight spatial constraints of an artificial island, a punctuation mark between sky and mud that has no natural right to exist in 20 meters of open water. The island would need to rise from the seafloor to a height sufficient to house the tunnel portal, the ventilation infrastructure, and the transition ramps, all while withstanding the same typhoon forces that shaped the bridge design. Nothing natural would provide a foundation, so nothing natural would be used. The steel curtain method begins with a ring. A single ring, 22 meters in diameter and 40 meters tall, fabricated onshore from steel plate 18 mm thick, its interior stiffened with radial ribs that give it the appearance of a giant industrial gear. This ring is floated to the designated coordinates, and then it is allowed to sink, guided by GPS and acoustic positioning, until it settles on the seabed. But the seabed is still that same 30-meter layer of tofu mud, and the ring's weight alone will cause it to sink unevenly, tilting past the point of recovery. The solution is to pin it in place with 68 steel piles driven through guide sleeves around the ring circumference, each pile hammered 40 meters into the competent soil below the mud. When all 68 piles are driven, the ring is no longer resting on the seabed, it is suspended from a cage of steel that transfers its load to the Pleistocene-era sands beneath. The ring is now immovable. 119 more rings must be placed in a precise ellipse, each one touching its neighbors to form a continuous wall, a watertight fortress 40 meters deep and 1,200 meters in circumference. The gaps between rings, measured in single centimeters, are sealed by divers working in zero visibility water, their only guidance the feel of steel against their gloved fingertips as they weld closure plates across the joints. When the steel curtain is complete, the dredging vessels move in sight. They pumped 12 million cubic meters of sand into the enclosed area, sand sourced from a borrow pit 50 kilometers away where the grain size has been analyzed to ensure optimal compaction. The sand displaces the seawater trapped inside the ring, rising above the surface in a brown slurry that slowly clarifies as the sediment settles. Within 6 months, an island exists where previously there was only open water. It is 625 meters long and 200 meters wide, shaped like a whale when viewed from above, its blunt end facing the prevailing current to minimize scour. On this island, the bridge will end and the tunnel will begin. The transition ramp descends at a 3,5% grade, the maximum that allows heavy trucks to maintain speed, and disappears into a rectangular concrete portal that looks like the entrance to a buried colossus. Which, in a sense, it is. The immersed tube tunnel is not drilled. The soft seabed makes tunnel boring machines impractical, the risk of the face collapsing into the mud too high to accept. Instead, the tunnel is prefabricated in the same megafactory that produced the bridge segments, cast in sections 180 meters long, 38 meters wide, and 11 meters high. Each section weighs 75,000 tons, a weight so abstract that the documentary illustrates it with a fleet of aircraft carriers stacked on a scale. The sections are cast in a dry dock, their ends sealed with temporary steel bulkheads, and then the dry dock is flooded. For the first time, these objects built on land become marine objects, bobbing in their flooded cradle with a draft of 10 meters. Tugboats maneuver them out of the dry dock and into a specially dredged channel that leads to the open sea. The journey to the tunnel site takes 18 hours at 2 knots, the floating behemoths drawing every other vessel to a halt as they pass, their sheer scale making the tugs that pull them look like bathtub toys. At the tunnel site, a trench has been prepared. The same mud that plagued the bridge foundations has been excavated from a 50 meter wide, 15 meter deep furrow stretching 6,7 kilometers across the seafloor. A gravel bed has been laid at the bottom, screed to a flatness tolerance of 40 mm across the entire width, an act of precision that required a custom-built underwater leveling rig operated by GPS and sonar. The tunnel section arrives and is positioned above the trench. Immersion pontoons, temporary structures mounted on the section's roof, take on water ballast, and the 75,000-ton concrete box begins to sink. The descent rate is controlled at 0.3 meters per minute, guided by cables attached to seabed anchors. As the section approaches the gravel bed, the precision requirements tighten. The mating face of the new section must align with the face of the previously placed section within a tolerance envelope measured in single-digit millimeters, all of this happening in water with visibility that ranges from poor to absolute zero, depending on the sediment load. The connection is made using a mechanism called the Gina gasket, named for the Italian engineer who designed it and bearing no relation to any human name beyond that happy accident. The Gina is a rubber profile that runs around the entire perimeter of the tunnel section's mating face, a continuous loop of neoprene 37 cm wide. When the new section is brought within 50 cm of the already placed section, the water trapped in the gap between them is pumped out. The external water pressure, 15 meters of head at this depth, acts on the entire cross-sectional area of the tunnel face, generating a force of several thousand tons. This force compresses the Gina gasket between the two concrete faces, deforming it by 80 mm and creating a seal so absolute that not a single drop of water penetrates. The temporary bulkheads can now be removed, the interior of the two sections becoming a single continuous space. What was ocean floor moments ago is now the inside of a highway tunnel, bone dry and lit by the construction crew's work lights. The 3D cutaway animation reveals the Gina in cross-section, its geometry shifting in response to the compression, and then goes further, showing the secondary Omega seal mounted on the interior face, a backup barrier that will remain dormant unless the Gina is somehow breached. The narrator notes that in the history of immersed tube tunnels, no Gina gasket has ever failed once properly seated. The tunnel under the shipping channel uses 33 of them. But the Gina gasket does something else, something that becomes viscerally important when the animation shifts to an earthquake simulation. The joint between tunnel sections is not rigid. The Gina allows for axial movement of up to 76 mm and lateral movement of up to 45 mm, accommodating the thermal expansion and contraction that comes with seasonal temperature changes and the slow creep of the seabed over decades. More critically, it allows the tunnel to flex during a seismic event. The animation shows a magnitude 7.5 earthquake originating from a fault 80 kilometers away, the shock waves propagating through the seabed and reaching the tunnel. The gravel bed liquefies briefly, the tunnel sections shift relative to one another, and the Gina gaskets compress and extend in a wave that travels the length of the structure. The joints hold. The tunnel survives. This is not theoretical. Immersed tube tunnels in Japan have survived Kobe-level earthquakes with nothing more than cosmetic cracking. The design has been battle-tested by the planet itself. 6.7 kilometers of tunnel, 33 sections, 33 Gina gaskets, and a single terrifying question that kept the fire safety engineers awake through years of design reviews. What happens when a tanker truck loaded with 30,000 liters of gasoline crashes inside this underwater tube? The fire that follows will reach temperatures exceeding 1,200 degrees Celsius. At that temperature, concrete doesn't burn but it does spall. Moisture trapped in the concrete matrix flashes to steam, creating internal pressures that blast chunks of concrete from the ceiling and walls, exposing the reinforcing steel. Steel loses half its structural strength at 600 degrees Celsius. At 1,200 degrees, unprotected rebar turns to spaghetti, and the tunnel roof above it collapses, opening a direct path for the ocean to flood the entire structure. This scenario is the nightmare, and it has happened before. The Mont Blanc tunnel fire of 1999 burned for 53 hours, killed 39 people, and reached temperatures that vitrified the tunnel walls into glass. The difference is that Mont Blanc was in a mountain, not under a shipping channel with millions of tons of water pressing down. The escape architecture begins under the road deck. The tunnel cross-section is not simply a box with traffic lanes. It is 3 boxes stacked and nested. The top level carries 3 lanes of traffic in each direction. Below it, separated by a fire-rated concrete slab 400 mm thick, runs the escape gallery, a 3,5 meter wide, 2,5 meter high corridor that extends the entire 6,7 kilometers. Every 270 meters, a staircase connects the road deck to this refuge, the stairwells pressurized with positive air pressure to keep smoke from following evacuees down. The escape gallery itself is pressurized to 50 pascals above the road deck, a differential that ensures that if a door is opened, the airflow is always from the safe zone into the fire zone, never the reverse. Fire-rated doors with a 2-hour rating separate the escape gallery into fire compartments, so that even if one section is compromised, the rest remains tenable. Ventilation towers rise from the artificial islands at both ends of the tunnel, 60-Meter tall structures that serve as the tunnel's lungs. In normal operation, they maintain air quality through a semi-transverse ventilation system that exchanges the tunnel's entire air volume every 6 minutes. In a fire, they switch to a longitudinal smoke extraction mode, activating massive axial fans that can move 300 cubic meters of air per second. These fans create an air velocity of 3 meters per second in the tunnel, a speed calculated to push smoke in one direction while allowing people to evacuate in the other. The critical number is 1,5 meters per second, the minimum velocity to prevent smoke backlayering, where hot gases roll along the ceiling in both directions. At 3 meters per second, the smoke stays obediently on one side of the fire origin, and the escape route on the other side remains clear. The emergency protocols were rehearsed 40 times before the tunnel opened, full-scale simulations with volunteer evacuees, real smoke generators, and timed evacuation drills. The target was complete evacuation of a fully loaded tunnel within 8 minutes of a fire alarm. The first drill took 14 minutes, and people were crying by the end, the confusion and claustrophobia and the sound of fire crackling through the smoke overwhelming even those who knew it was a simulation. The 40th drill took 6 minutes and 47 seconds. The volunteers walked calmly to the nearest staircase, descended into the brightly lit escape gallery, and followed the green photoluminescent guidance strips to safety, the 2-hour fire doors closing behind them with a resonant thud that sounded, one participant said later, like God closing a book. The ventilation fans roared overhead, the smoke moved precisely as modeled, and when the drill controller called the all clear, the tunnel sat empty and silent, its safety systems having performed exactly as designed. The engineers monitoring the drill didn't celebrate. They noted 3 minor deviations from the plan and scheduled a 41st drill for the following month. The crack appeared on a Tuesday morning, during a routine ultrasonic inspection of a test weld on segment 47. Segment 47 was not yet installed, it was still in the casting yard, curing under controlled conditions, waiting for its turn on the tieni. The weld in question joined 2 internal stiffener plates, a detail so mundane that it appeared on 3,400 separate locations across the bridge's structural drawings. When the technician ran the phased array probe along the weld bead, the screen lit up with a pattern he had seen only in training manuals. A crack, 47 millimeters long, propagating along the fusion line between the weld metal and the parent steel plate. It was subsurface, invisible to the naked eye, and it should not have been there. The protocol for such a finding was clear: document, report, convene. Within 4 hours, the lead engineer was standing in front of a conference table surrounded by the project's senior metallurgists, welding specialists, and quality assurance managers. Someone had printed the ultrasonic scan and taped it to the whiteboard. The crack showed as a thin red line, a seismograph of failure, against the blue background of sound steel. The immediate question was whether this was an isolated defect or systemic. If isolated, segment 47 could be repaired and the project would absorb a 2-week delay. If systemic, every weld of this type across the entire project was suspect, and the bridge was, in a very real sense, unbuilt. The metallurgists requested a destructive test. A section of the weld was cut out, a 300 mm cube of steel that required 6 hours of diamond wire sawing to extract. The cube was shipped to an independent laboratory, where it was mounted in a scanning electron microscope. The images that came back revealed the full horror. The crack had initiated at a microscopic inclusion, a speck of slag smaller than a grain of sand, that had been trapped in the weld pool during fabrication. Around this inclusion, hydrogen atoms had migrated over weeks of curing, concentrating at the grain boundaries of the steel's crystalline structure. This was hydrogen-induced cracking, also known as cold cracking or delayed cracking, a phenomenon so insidious that it had been the subject of welding codes for half a century. The codes mandated preheating of the steel to drive off moisture, low hydrogen electrodes stored in heated quivers, and post-weld heat treatment to allow hydrogen to diffuse out. Somewhere in the chaotic reality of fabricating 340,000 tons of steel, a welder had picked up a rod that had been exposed to humid air for too long, or a preheat cycle had been shortened to meet a production deadline. Or a post-welt inspection had been rushed, and a hydrogen atom smaller than anything visible had found its way into the steel, and then another, until their collective pressure had torn the metal apart from the inside. The lead engineer did not sleep that night. He sat in his office with the door closed, the ultrasonic scan spread across his desk, a calculator he didn't trust, and a satellite phone that he used to call a welding expert in Norway who owed him a favor from a previous project. The Norwegian listened to the description, asked 20 minutes of technical questions about heat input rates and diffusible hydrogen content, and then said something that made the lead engineer's stomach drop: "If you found one, there are more. Hydrogen cracks don't travel alone." The call ended. The lead engineer stared at the ceiling for a long time. Then he made 3 decisions that would either save the project or end his career. The first decision was total transparency. He called the project's government oversight committee and told them construction was suspended pending a full investigation. The second decision was total audit. Every single welt on every single completed segment would be re-inspected using time-of-flight diffraction ultrasonics, a more sensitive technique than the standard pulse echo method, requiring specialized technicians who would have to be flown in from Europe and Japan. The third decision was the hardest. If the systemic hypothesis was correct, some percentage of completed segments would need to be cut apart and re-welded, a process that would cost tens of millions and delay the project by months. He authorized the procurement of replacement steel before the audit results were even in, committing funds the project didn't have on the gamble that he was right. The audit took 3 weeks. The technicians worked 20-hour shifts, sleeping on cots in the fabrication yard, their ultrasonic equipment beeping through the night like a hospital ward of mechanical patients. They found 23 additional cracks across 17 segments. All were subsurface. All were hydrogen-induced. All were located in the same type of stiffener welt. The pattern was clear: 1 welding station, 1 shift, 1 supply of electrodes that had been improperly stored. The affected segments were identified, quarantined, and scheduled for repair. The electrodes were traced to a specific supplier batch and recalled. The welding procedure was revised to require redundant preheat verification and extended post-weld hydrogen bakeout. The lead engineer stood in front of the oversight committee and presented the findings. When he finished, the committee chair asked a single question: "Can you guarantee this bridge will stand for 120 years?" The lead engineer paused. The camera holds on his face, the exhaustion visible in every line. "I can guarantee," he said, "that we have found every crack we know how to find, using every tool that exists. The rest is faith in the steel. And I have that faith." The committee voted to continue. The repairs took 4 months and cost $87 million. The lead engineer visited segment 47 personally on the day it was finally cleared for installation. He stood in front of the repaired stiffener, running his bare hand over the ground-smooth surface of the new welt, and said nothing. A photographer captured the moment. The photo would later hang in his office, a reminder of how close the impossible had come to becoming the disastrous. The final section was slotted into place on a night in late autumn, the weather window so narrow that the operation had been postponed 7 times in the preceding month. The Tianyi lifted the last 8,000-ton box girder, swung it through the darkness with its positioning lasers cutting green lines through the sea mist, and lowered it into the 15mm gap. The locking pins engaged with a sound that carried through the structure's entire length, a metallic clunk that the workers on the adjacent segments felt through their boots. Someone uncorked a bottle of something that wasn't champagne. The celebration was unofficial and brief, because the bridge was not yet a bridge. It was a sculpture of concrete and steel that still needed to prove it could hold together under its own weight and the weight of everything that would cross it. The LED light test happened 3 months later, after the electrical systems had been commissioned and the control software debugged. The lighting designer, a specialist who had previously illuminated stadiums and skyscrapers, had conceived the bridge not as a transport structure but as a horizontal sculpture. The fixtures were mounted along the entire 55-kilometer length, RGB-capable LEDs programmed to shift color temperature with the time of day, warmer at dawn and dusk, cooler at midday, a circadian rhythm for a structure that would never sleep. When the test command was sent, the effect propagated outward from the control center in a wave, the lights igniting segment by segment at a speed just slow enough to track with the human eye. From the aerial camera, the bridge looked like a dragon of neon and glass, its S-curve suddenly made visible in the darkness, a calligraphic stroke of light across the black water. The engineers watching from the control room were silent. The lighting designer was not. He was weeping, unashamit, the culmination of 7 years of work reduced to something so beautiful that the engineering seemed incidental. The first car crossed at 3:17 Uhr nachts on the day of the official opening, a convoy of 3 vehicles carrying the project's senior leadership. The lead engineer sat in the front passenger seat of the first car, a man who had spent 13 years of his life on a structure he had never traveled end to end. The driver maintained exactly 100 kilometers per hour. The tunnel approached, the transition from bridge to artificial island marked by a subtle change in road surface texture, and then the car was descending into the illuminated bore, the tiled walls flashing past in a rhythm that felt like traveling through the chambers of a gigantic heart. The tunnel was silent except for the hum of tires on asphalt and the distant whisper of the ventilation system. No radio. No conversation. The lead engineer watched the tunnel walls, counting the joints in his head, picturing the Gina gaskets compressed behind the tile, the escape gallery running below, the ventilation fans spinning in their shafts. At 4:02 Uhr nachts, the car emerged on the far side. The driver pulled over at the first safe location, and the lead engineer got out. He stood on the shoulder of the bridge, looking back at the structure he had built, the lights stretching away into a distance that the human eye couldn't resolve. A colleague asked him what he was feeling. He thought for a long moment. Tired, he said. Then he got back in the car and told the driver to continue. The first year of operation answered the question that the politicians had been asking since before the first caisson was hammered into the mud. Was it worth it? The traffic numbers exceeded projections by 22%. The crossing time between the two economic zones dropped from 4 hours by ferry, subject to weather cancellations and seasonal typhoon closures, to 31 minutes by bridge, 365 days a year. The economic impact models, the ones that the project's critics had dismissed as fantasy, turned out to be conservative. Supply chains that had been bottlenecked by the ferry schedule reorganized around the bridge's continuous availability. Commuting patterns emerged that had never been possible before, workers living on one site and employed on the other, their daily round trip suddenly feasible. The bridge was not just a structure. It was a reorganization of human geography, a rewiring of economic possibility that would compound for generations. But the climate models were also being revised. Sea level rise projections for the region, updated in the years since the bridge's design was finalized, showed a more aggressive trajectory than anticipated. The 120-year design life had incorporated a certain amount of sea level rise, but the new numbers pushed closer to the margin. The artificial islands had been built with a freeboard that assumed a worst-case scenario. The new projections suggested the worst case might arrive sooner. Storm surge modeling for a Category 5 typhoon in 2100 showed water levels that would overtop the island's sea walls by 40 centimeters, not enough to destroy the structure but enough to flood the tunnel portals if the floodgates failed. The bridge was an engineering response to a stable set of physical assumptions. The planet was demonstrating, year by year, that stability was not guaranteed. The engineers who built it knew this. They had designed as conservatively as the budget allowed. The question that hung over the dedication ceremonies was whether conservatism in 2010 would prove sufficient in 2070. The camera lingers on the faces. Not the politicians who cut ribbons or the dignitaries who gave speeches, but the others. The welder who worked 28-day shifts for 6 years and missed the birth of his second child. The crane operator who moved 2,700 segments without once exceeding the 3 mm tolerance. The concrete technician who stayed awake for 18-hour pours, his eyes burning from cement dust and Halogenglare. The cook on Platform 3 who fed 800 workers 3 meals a day in a kitchen that never closed. The nurse who treated welding flash burns and salt-induced dermatitis and the quiet despair of men too far from home. The engineer who found the crack and the engineer who stayed up all night deciding what to do about ET. The child of a worker who drew a crayon picture of a bridge that her father was building, a bridge that in her drawing reached all the way to the moon. The faces fill the frame, one after another, a mosaic of human effort that redefines what the bridge actually is. It is not steel and concrete. It is 30,000 human lives compressed into 55 kilometers of structure, each bolt and welt a frozen moment of someone's attention, someone's exhaustion, someone's sacrifice. The final shot is from a helicopter orbiting at 1,500 feet as the sun sets behind the bridge. The S-curve catches the golden light, the towers throw long shadows across the water, and the traffic moves in both directions, a river of headlights flowing toward the vanishing point where the bridge merges with the curvature of the earth. The narrator speaks for the last time. We built it not because it was easy, but because we are human. And for us, the horizon is never a boundary. It's an invitation. The screen fades to black, but the afterimage of the bridge remains, the neon dragon imprinted on the retina, a thing that should not exist and yet does, because someone imagined it and then refused to stop imagining it even when the mud was too soft and the wind was too strong and the cracks appeared in the steel. The impossible, it turns out, is just a longer timeline.